Good morning, everyone. I am Vinita, working as an associate professor in the Department of Electrical and Electronics Engineering, RMD Engineering College. Today in this video, I am going to explain about standing waves and natural frequencies in power system transients. We all know that in power system, we have a generation side as well as the distribution side. So whatever the power generated, that will be equal to the power drawn. But whenever there is a mismatch of impedance between transmission line and load, the reflections will occur in the power system. And if the incident signal is a continuous AC waveforms, these reflections will mix with more of the oncoming incident waveform to produce a stationary waves called standing waves. That is, if the input signal is continuous, then what will happen means the reflections started from the circuit will be reflected continuously, and that will be producing a waveform called as standing waveforms. Let us see the definition for natural frequency. Natural frequency is the frequency at which a system oscillates when it is disturbed. The systems will have the inertial and elastic characteristics which makes them want to oscillate or vibrate at certain frequencies. These specific frequencies are termed as natural frequencies. When two waves have same wavelength, same amplitude as well as in phase, but both the waves are traveling in opposite direction, then the resulting wave does not appear to move. Rather, it oscillates in its place itself. This wave that will be termed as standing wave. And the best example for the standing or stationary waves are nothing but the string, guitar string. That is, whenever the guitar is operated, there will be an vibrations between the sending end as well as the receiving end. And here in this vibration or in the string, there will be two notes. That is, two notes at the starting point as well as the ending point. So what is meant by node? Node is nothing but the point where the particles are not moving at all. That is called node. That is, here, this is the node point. Here, the particles which are all not moving. But we have an under definition called as antinode. So where all the particles that will be moving continuously, that is termed as antinode. So depends upon the number strings, we'll have the nodes as well as antinodes. By means of traveling wave and standing wave concept, the behavior of electrical quantities at power frequencies on the distributed line is explained here. That is, in order to explain the standing wave as well as natural frequencies, we are going to consider a distributed line for analysis purpose. And here, the time variation of all the voltages and currents was sinusoidal at a fixed frequency. Since these waves, that is the voltage as well as the current waves that travel from source to the load end as an electromagnetic waves with finite velocity, it will take a short duration to start from the source end and to reach the load end. And here in this distributed line, the parameters like R, L, G, C per unit length that will be distributed along the entire length of the transmission line. And here, in order to derive the expression, we can consider this small diagram for the transmission line. In this equivalent circuit, we have a capacitance as well as inductance, distributed capacitor as well as the inductance. Since it is considered only for a small element delta x, the capacitance will be represented by delta x, C into delta x. And similarly, the inductance can be represented by L into delta x. From the load end towards the source side, the distance considered is nothing but capital X. And here, this is nothing but from this point, very small element delta x that will be considered. And the current flowing through the system is nothing but Ix. And the voltage at the receiving end is VR, and the current at the receiving end side is IR. And here, this will be divided into two sections. One is nothing but the part of inductance, another one is nothing but capacitance. So from the second diagram, At both ends of the inductive circuit, the voltages are represented by Vx plus delta into Vx. That is at the left hand side. And if you take the right hand side, the voltage will be taken as Vx. Similarly, for the capacitance, at both ends, we have to mark the current values. So for the left hand side of the capacitance, the current is denoted as Ix plus delta into Ix. In the right hand side, it is denoted as Ix. Let us see the variables that is taken for this analysis purpose. Capital L, that represents the total length of the transmission line, and small l is nothing but the distributed series inductance, and small c is distributed shunt capacitance. L into delta x, that is equal to inductance of differential length delta x, that is for a smaller length delta x, the inductance is equal to L into delta x. Similarly, the capacitance for a differential length delta x can be taken as C into delta x. And here, the voltage of on two sides of the line already it is shown in the figure. And from the figure, we can write the expression as Vx plus delta into Vx minus Vx. That is both ends of the inductor we have to take. It is represented as Vx plus delta into Vx minus Vx, that is equal to delta into Vx, because here this plus Vx and minus Vx get cancelled. So its value is nothing but delta into Vx. And we know the formula for V. V is equal to I into Z. So this is Ix into Z is equal to omega, J omega L. And for a small distance, delta X, the formula that is we have to multiply I into Z with delta X. And then Ix plus delta into Ix minus Ix. Again here, this Ix and Ix get cancelled, and delta X, that is equal to J omega C into delta X into Vx. And here, the value of delta X, that will be very small, and so that this delta X can be written as dVx divided by dx. From the previous expression, from this expression, we can write delta Vx divided by delta X is equal to J omega L, J omega Ix, J omega L into Ix. And here, since this delta Vx, that is very small value, we can replace this delta Vx by delta X by dVx divided by dx, where J omega L can be written as Z. So the expression can be written as Z into Ix. Similarly, from the previous current equation, from this equation, delta Ix divided by delta X, that is equal to J omega C into Vx, where J omega C is nothing but Y. And we can write the expression as dIx divided by dx, that is equal to Y into Vx, where Y is equal to J omega C at power frequency. So by differentiating the above two equations with respect to x, and so that we will get the expression like this: d square v by dx square. So first expression is dv by dx. If we differentiate the expression with respect to x, we will get d square v by dx square, that is equal to z into dix divided by dx. So that is equal to z. This z we can maintain as constant. This dix divided by dx is nothing but y into vx. Already we have derived the same expression. Now, this zy can be replaced by p square, because here p is nothing but the propagation constant. So the formula to find out p is equal to square root of z into y. So if it is p is equal to square root of zy, what is p? What is zy? Zy is nothing but p square. So we can replace this zy by p square. Therefore, d square vx divided by dx square, that is equal to p square into vx. Next, similar to this voltage equation, we can derive it for current equation. So d square ix divided by dx square, that is equal to y into dvx divided by dx, where this dvx, this term can be replaced by, if you substitute the value for dvx divided by dx, you will be getting z into ix. Already we have y. So the expression can be written as z into y into ix. Now, what is this Z into Y? It is P square. So we can write D square Ix divided by Dx square, that is equal to P square into Ix. So this is the expression for D square Vx by Dx square and D square Ix divided by Dx square. Since here there are two variables x and s, we can rewrite the expression as dou v by dou x of x comma s, that is equal to z of s into I of s x comma s. Similarly, dou I of x comma s divided by dou x, that is equal to y of s into v of x comma s. Now, the solution for the above two equations are v of x is equal to a into e power px plus b into e power minus px. And similarly, I of x is equal to p by z into a into e power px plus b into e power minus px. From this, if we substitute the value for p, and again, if you rewrite the expression, we will be getting square root of y by z into a into e power px minus b into e power minus px. Now we know that the surge impedance Z0, that is equal to square root of y by z, and this square root of y by z. So we have another one expression for Z0, that is equal to L by C. So if you substitute the value for all those things, we will be getting this expression. Now, in the previous equation, we have to substitute the initial conditions and we can find the value of A and B. So A becomes 1 by 2 into VR plus Z0 into IR. And B is equal to 1 by 2 into VR minus Z0 into IR. So these two are the expressions for A and B. So after calculating the value of A and B, we can substitute these two equations in Vx and Ix. So if you substitute the value of A and B in Vx and Ix, and if we simplify the expression, we will be getting two equations like this. Vx is equal to 1 by 2 into VR plus Z0 into VR plus Z0 into IR into e power j2 lambda x divided by lambda plus 1 by 2 into VR minus Z0 into IR into e power minus j2 lambda x divided by lambda. Similarly, the expression for Ix. And from this, these e power j2 lambda x by lambda can be rewritten as Vx into cos 2 pi x by lambda plus j into Z0 into IR. That is, after the simplification, this is the final expression for Vx and Ix. Now, these two expressions can be drawn or can be shown in the waveform. So, for this, we can take these two equations, that is equation 9 as well as 10. So, if you take equation 9, this is your first part, this is the second part of equation 9. Similarly, this is the first part of first equation and this is the second part of the second equation. So, for this, in order to draw these two, draw the waveforms, we can make use of these two expressions, Vx and Ix. So, if you take the first equation, that is voltage equation, the first part of this equation is Vr into cos 2 pi x by lambda. And the second part is J into Z0 into IR into sin 2 pi x by lambda. Now, if we can take the first part and substitute two boundary conditions like x is equal to 0 and x is equal to L. So, first we can apply x is equal to 0 in this first part. If you substitute x is equal to 0, what will happen? Cos 0. Cos 0 is nothing but 1. So the magnitude of this first part is nothing but VR. Similarly, we can substitute x is equal to L. If you substitute x is equal to L, your expression becomes VR into cos 2 pi L by lambda. Similarly, you can take the second part of your first equation. So J into Z0 into IR into sin 2 pi x by lambda. So if you substitute x is equal to 0, what will happen? Sin of this term becomes 0. Sin 0, 0 means the entire terms become 0. This is the first boundary condition. And if you substitute x is equal to L, our expression becomes Z0 into IR into sin of 2 pi L by lambda. Similarly, we have to take our second equation, that is second equation is your current equation, and you can apply the same two conditions like x is equal to 0, what is the magnitude of Ix, and x is equal to L, what is the magnitude. Similarly, in the second part also, we have to substitute these two boundary conditions, x is equal to 0 and x is equal to L. Now, with these representations, we can draw the standing waveform. So first one, the first part is VR in VR. So if you substitute x is equal to 0, the magnitude is VR. So this is the magnitude VR. So actually, we have to start it from the load side. That is, it is the here it is given actually the voltage Vx at any point x on the line from the load end. So here this is also from the load end. So from the load end, if x is equal to 0, the magnitude is VR. And then if x is equal to L, then what is your magnitude? VR into cos 2 pi L by lambda. So VR into cos 2 pi L by lambda. So from the distance of source load in towards the source end. Now, if you add these two vectors, we can calculate the sum of, if you add these two vectors, we will be getting the total vector VR plus, that is for the condition of x is equal to 0 and x is equal to L. Similarly, this is the waveform that is drawn for current equation. That is first part of the current equation. If you substitute in this equation, if you substitute x is equal to 0, the first part becomes IR and the second part becomes, if you substitute x is equal to 0 means the second equation is 0. And if you substitute x is equal to L, we will be getting the magnitude of IR into cos 2 pi L by lambda. If you substitute x is equal to L, we will be getting VR by Z naught into sin 2 pi L by lambda. Now that condition that is also substituted and the waveform that has been drawn from the distance, that is from the load end side, we can consider length L, and when x is equal to 0, the magnitude of current is IR, and then for x is equal to L, the magnitude of current is IR into cos 2 pi L by lambda. Now we can, if you add these two waveforms, we'll be getting the overall waveform. So for this, to draw the vector diagram, we have to take any one vector as the reference vector. Here, the voltage waveform VR that is taken as the VR that is taken as the reference vector. And here, this wave, that is this voltage vector, corresponding voltage vector, that will be see here. We can draw the equivalent circuit here. For this, first we need to take the reference vector VR. This is the reference vector VR, and this is also the voltage vector VR that will be less than the value of magnitude VR, but it is also VR. It is just like the voltage drop. So this voltage that will be also lies in the same phase. So this is VR, this magnitude, and this is also VR, but the magnitude of VR, which is less than the value of this magnitude VR. So both the voltages will be lies in the same phase. For the same vector, its corresponding current for an inductive circuit with which lag behind the voltage by an angle of theta L. And similarly, here the second vector is nothing but I naught into cos 2 pi L by lambda. And here I naught is, that is Z naught into I naught is nothing, IR is nothing but the reactive drop actually. This reactive drop that will be perpendicular to this voltage vector. It is not exactly perpendicular, but it is greater than it. It will be greater than. It is not greater than or less exactly 90 degree, but it will lead the voltage vector by some angle. So this is this IR vector. This is the first vector diagram. And similarly, we can draw the vector diagram for the second case. For the second case is nothing but That is second part of your voltage vector as well as second part of your current vector. And if you redraw like the first case, if you redraw the vector diagram for the first and the second case, so we can go for this for second part. X is equal to 0 means the value of voltage is equal to 0, and its magnitude is if X is equal to L means Z naught into IR into sine 2 pi L by lambda. This is for the first expression, 0 and Z naught into IR, 0 and Z naught into IR into sine 2 pi by 2 pi L by lambda. When X is equal to 0, when X is equal to 0, the magnitude of VR that is equal to 0. When X is equal to L, the magnitude is nothing but Z naught into IR into sine 2 pi L by lambda. So if you join these two terminals, we can draw the vector diagram. Similarly, for the second equation, for the current equation, if you substitute X is equal to 0, the magnitude of IR that is equal to 0. If you substitute L, X is equal to L, we will be getting the magnitude of VR by I naught into VR by Z naught into sine 2 pi L by lambda. So V by Z is nothing but I actually. So here, now if you join these two vectors, we will be getting that is overall vector diagram. So for this again, we can take VR as the reference vector. So VR is nothing but this is VR, and then here for the corresponding voltage vector, its current lag behind the voltage by an angle of theta or phi. And here, if you take this current vector, if you take the current vector, it is nothing but IR into its corresponding current vector is IR into cos 2 pi L by lambda. And here the magnitude of this IR and this IR into cos 2 pi by lambda, both will be current vectors, but this current vector that will be the magnitude of this current vector that will be less than the value of this IR. So both will be in phase. And similarly here, this VR by Z naught, that is nothing but reactive drop. It will be perpendicular to this voltage vector. So it has been drawn like this. This is the overall vector diagram for this second part of the two equations, voltage as well as the current equations. So this is about standing waves and natural frequencies in power system transients. Thank you.